My name is Thomas Thuruthel. I'm an assistant professor at UCL. And in this talk, I will be giving a pitch for why machine learning goes hand in hand with soft robotics, especially when it comes to dynamic tasks. So we have seen the rise of AI, particularly in the last few years. It's kind of exciting and also scary at the same time. And it's largely being brought forward because of the amount of data that is being put into it and the amount of diverse data that we have available. And we have seen that in this general AI field dealing with languages and vision. We are slowly seeing that in robotics as well. So this is the robot transformer X, which used a lot of diverse data from a lot of robotic manipulation tasks and has generated a language mediated model, which is applicable to a lot of general robotic structures. So here you can see these systems being able to use the same control policy to do multiple tasks on different robot morphologies. So this is clearly remarkable in what it can do. You don't need any sort of training afterwards. So it's just a big neural network that you can download off the net and then test on your own. So clearly, the field of big data in AI is slowly permeating to robotics as well. But what you can see here is that these are still limited to kinematic controls. And what I mean by that is all the tasks that you see are essentially only pure kinematic control of the tip. And that's why they're able to generalize to a lot of robots. They completely ignore the dynamics of the robot itself. That's why you need any prior knowledge about the system, which is still good. But it does restrict what kind of tasks you can achieve in real world. If you want to go to more generalistic robots and you want to tackle a lot more challenging problems, then you need to think of dynamic control policies. And this is not that trivial in robotics, primarily because simulations are not that reliable. So simulations that can capture the full dynamic range of robots, especially when they're interacting in the environment, is not that easy. And if you were to collect data from real world, then there is a problem of safety and reliability. So it's not easy for us to set up a robot, make it do a lot of tasks for a long period of time, and have a guarantee that things won't go wrong and things won't get damaged. So that's a quite big challenge, and that's why we are not yet there where we can have a single controller for all the different type of robot morphologies that can do really fast dynamic tasks. So my talk is primarily an argument that if you want to go towards these kind of learned dynamic control policies, then soft robotics is the way forward. And I'm going to convince you with 3 arguments, which and I'm going to back it up with work that I have been involved in. The 3 arguments are that soft robots have a very set of order dynamics, and I'll come to what that means later. They enable smooth and safe interactions, and they also have a more repertoire of sensory data, which makes it possible to have diverse data so they can train your models. Right, so let's start with order dynamics and what it means. So if I were to give you these 2 models, on the right side, we have a very simple rigid tooling manipulator, and on the left, you have a soft. They have more or less the same degrees of actuation. So this double pendulum is 2 actuators, and on the left, I can tell you that it has only 3 actuators. But if I were to ask a roboticist which of the system is complex to model, clearly everyone would say that this soft manipulator would be more difficult to model. And that is true. It's more non-linear. It has more passive degrees of freedom than simple pendulum. But if I were to ask the same question to a black box machine learning model, it turns out that the left side dynamics is much easier to learn than to learn the dynamics of a double pendulum. Why is that? One of the main reasons is because even if there is a double pendulum, if you don't have friction or damping, it exhibits chaotic behavior. Which what that means is that slight changes in initial conditions would lead your behavior to change drastically, and that is not suitable for learning-based algorithms. It causes instability in learning, whereas soft robots exhibit the opposite sort of behavior. And so in this work, which was done during my PhD, we show that these soft systems exhibit large number of dynamic attacks. What that means is that irrespective of initial conditions, to dynamic tasks, these soft robots tend to have a lot of limit cycles or dynamic attractors. So here you can see this soft robot tracking a circular trajectory, completely open loop, and any irrespective of what disturbances you apply, they would go back to the same trajectory. Here it's a very simple circular trajectory, so that this can be done for a lot of various trajectories. You can find infinite trajectories that exhibit this behavior. And the cool thing is, it also goes back to this limit cycle with millimeter precision. Even though it's soft, it has a lot of hysteresis friction. As long as you're moving fast, as long as you're not in the static friction regime, things are very repeatable, very predictable, which is again something that you don't associate with soft robots. So it turns out that even for this complex manipulator, so here we made a physical prototype of a soft robot which has 6 actuators. It turns out that you can learn a fully dynamic model of this soft robot with just only 40 minutes of data, which is cool. It also turns out that the learned model is very stable. So if you could have in this graph, we show that a completely open loop prediction. Also here, the system is trying to predict how the tip of the robot will move, given the forces that you're applying over time. And you can see even for a long period of even 100 seconds, your predictions are not diverging from actual data, which is again remarkable that we've never observed in rigid robots. And it also turns out that you have pneumatic actuation, which means that you get direct access to force information. It's a small nuance. It is not that easy to get force-controlled systems in rigid robots, so that makes it also easier to learn this typing. Further on, recently we also show that we can even make it the problem more complex, and still it's feasible. So here we have similar called flip-flop, pneumatically actuated as well, slightly smaller in shape. It exhibits very nice dynamic behaviors. And here we're trying to learn a model which is more higher dimensional. So in the previous example, we're just learning the tip position. We're just trying to predict the whole shape as an image itself. And you can see the blurred images are the predictions by a deep neural network. And then we can use that to develop a control class. Quickly going through some of the results that we see. So again, the blurred ones are the predictions by a deep neural network. There are still some errors, but you can see that it still does decently well. And all you need is a few hours of data to learn this fully dynamic model without any prior knowledge. So we're not using any prior knowledge of the system. And you can use that model to do a much nice control task. Out of time here. Cool. So my second argument is about the fact that soft robot enables smooth and safe interactions. And this is a bit trivial to understand. And I can explain it further better through this example. So here we have an anthropomorphic soft hand with some embedded sensors. These are pneumatic sensors. They measure the pressure in small cavities. So we had the task of getting a lot of this sensory data when it comes to manipulation tasks. And in order to do that, Kiran was the primary author of this paper, who's you can see here. He is teaching the robot by demonstration how to pick up an object. The hand itself is completely passive. And because of its passive nature, you can do some clever interactions so that you can pick it up without any actuation of the hand itself, but purely by the actuation of the base of the hand. And one single demonstration is enough for kinesthetic teaching. And then we can set the robot to do the task by itself for a long period of time. We can add some variability in the motion so that we can get diverse sensory data. And this is quite safe and reliable. So you can keep this running forever, at least for 2 to 3 days, get a lot of sensory data. And in this work, we then use this data to predict when things go wrong. So we developed a model which, based on purely only the tactile data, predicts if the object will fall out of hand. I'm not going to go into details of that, but the main message is, because of the morphology of the hand, or because of the soft interactions, it became very easy to collect a lot of data where we can see how minute variations in sensory data over time can help predict failures. And because the motions are predefined, we can even predict failures much ahead of time. So looking at small features, we can have a quick estimate of failure, which then further allows us to correct for this failure. So in the end of this video, you'll see that the model predicts failure before it happens, and then we're able to take corrective actions so that we can recover from failure. And again, this is all done without any prior knowledge of the system, one demonstration, and everything else is then completely autonomous. So which is not that easy if you have a rigid system. And I'll come to my last argument, which is that soft robots enable us to have a lot more sensory modalities attached to it, and which further means that you have more rich and diverse sensors for your models to learn from. And I think we have covered this a lot in this conference as well. And one of the things that I think is most exciting is the development of tactile sensors using soft technologies. I won't go into details of this much. I'm probably not the expert on this. I will just quickly show one of the work that we have done, which I find quite exciting, is this thin tactile sensor developed by David Hartman, which gives a very high resolution sensing without any electronic components. It's completely transparent as well. It can be made as thin as you want. It can be stretched to any shape also. Works on the principle of impedance tomography. And you can get maps of what is happening to this game. And if you can attach it to a system, then you can get more information about the task as well. And clearly, tactile information is important for interaction tasks, and it will become more and more important when you do dynamic tasks. And I believe soft technologies are the way to enabling this sort of sensory modality. Yeah, that's where I will conclude my talk. So recap: so soft robots enable order dynamics, smooth and safe interactions. So we have less of a discrete contact dynamics, and then you also get a wide range of sensory data, which is not feasible using traditional rigid sensor technique. I'm sure there are furthermore. I'll be happy to hear your thoughts as well. If you have any questions, contact me in this email. Thank you.